Okay, so welcome back. In this video we'll be solving basically this problem, which is about a refrigerant liquid that enters a condenser of a residential heat pump at a certain pressure and certain temperature, so 800 kilopascals, 35 degrees Celsius, and they give you the mass flow, which is 0.018 kilograms per second. Leaves at the same pressure. That's traditional because condensers and evaporators always work at constant pressure, and tell you the liquid is at the state is saturated liquid. If the compressor consumes 1.2 kilowatts of power, determine the coefficient of performance of the heat pump and the rates of absorption in the outside air. So that will be Q sub L over here. All right. So like always, I always say this part is actually part of the solution. You should always try to do some type of figure. So I like over here, I will do, this will be the condenser. Now this will go here to a compressor. You can do different figures. This is generally the figure that I do for a compressor that shows this compresses. Then we can go down over here again, and we have now this side the evaporator. Then on this side we actually have the valve. There's different ways to do this. Alright, so this is the valve. This will be the compressor over here. And a compressor always requires work or power in order to run. So we can say power in over here, and that in the problem has the value of 1.2 kilowatts. What else do we know from the problem? Is that, let's see, we have this. So, alright, so let's do here Q sub low. Let's do on this side Q hot. And then let's see what do we know here. We know the pressure is 800 kilopascals with a quality of 0. Here the pressure is P equal to 800 kilopascals. So it says will be 1 and 2 over here. So this will be P2 x2 P1, and we know T1 will be equal to 35 degrees Celsius. Now I don't think it's needed, but what happens on the expansion valve? If needed here, the enthalpy, remember, before entering the expansion valve and after should be the same. So the mass flow rate of the system, so this is going in this direction. So the mass flow on each element is equal to 0.018 kilogram per second. Alright, so, and what do we need to find? We need to find the coefficient of performance of heat pump, and we need to find the rate of absorption, which will be Q sub L. Alright, so first let's see, what is a heat pump? So I think that's important. Heat pump, because actually heat pump and refrigeration cycle are kind of similar. So let's say here we have a heat pump system. Heat pump system. Any system needs to operate between a hot and a cold reservoir. So heat pump is actually this part over here. It's the part of removing heat from the system. The refrigeration is actually putting cold into the system over here. And for either one, this is going to require that we put power into our system. So the system over here is this one over here. So by definition, what is the coefficient of performance or the efficiency of any system? So coefficient of performance is whatever we're trying to achieve, which in this case is heat pump, means remove heat from the system, so Q dot hot, divided by the amount of work that you put inside the system, or amount of electricity in this case. So this should be our first equation over here. Alright, so let's say it will be our equation Latin 1. Alright, so first part we need to define is the coefficient of performance. So that's obviously not enough information. However, what else do we know? So if I look at the condenser system, so if I just do here feature of the condenser, what do we have? So we know this is 1, this is 2, and we see right away that P1 is equal to 800 kilopascals, and that T1 is equal to 35 degrees Celsius. P2 will be equal to P1, and here basically what I tell you is that it's saturated liquid state over here. And what I'm trying to find here is the Q dot sub H. Alright, so let's see, we have everything. It looks like we have everything over here. So maybe we can remove this figure. And let me try maybe to zoom in a little bit. Oops, that should be fine. Okay, so for this control volume system, we are over here for this control volume. So let me write down for above control volume. We can write down the the first principle of thermodynamics, which will be basically this plus mH1 should be equal to mH2. So in this problem, for this system, the condenser, as you can see, there is no any power going in or out. And this one should be Q sub hot. So from here we can write down that Q sub hot will be equal to M, the mass flow, H2 minus H1. Alright, so I think conceptually this problem is almost done. So now what can we do? So combining the equations 1 and 2, what do we have? Let's see. So what was the first equation? Our first equation we derived was the one for the coefficient of performance, that is equal to coefficient of performance equal to the Q dot hot divided by the power. So now if we use the second equation, what will be the Q sub hot? Will be M dot H2 minus H1 over the power required. So I think that's basically all the problem, but now we need to go and find the correct values in the table. So we need to find H1, that will be over here. We need to find H2. So in order to know to which table to go, maybe let us do here a little figure. So let's say this will be, since we use constant pressure, let's do a T, V, or U over here. So we are right here. We are going through a line of constant pressure. There we go. So we know P1 equals P2 equal to 800 kilopascals. So we actually know what is the state at 2. So state at 2 will be saturated liquid, so will be right here. This is 2 over here. Okay, so let's find out what is the state at point 1. I'm guessing it's right here, okay? But instead of guessing, let's just go and try to go to the appropriate table. So for that, let's see if I can do it here at the bottom, so I don't have to go back on the page. So let's say we go to table A12, I think it is, and we look at the pressure P equal 800 kilopascals. So basically what I'm trying to find out is what is the temperature here, what is the saturation temperature given on the table. Okay, so that temperature over there is equal to, let's see, table A12, I have it right here. So table A12, let me try to zoom in. This is the saturation temperature, wrong direction. So I800 is 31, I don't know if you can read it, 31.31. So I can put it here, 31.31. And what do we know? What is the temperature actually at T1 is 35. So that means we are above this line. So this is not going to be to scale, but let's say this will be our state 1. So this is T1 equals to 35. Okay, and the temperature at state 2 then will be 31.31. Alright? Okay, so now we need to find out, so this could be V, U, or H. So from this figure, basically, now we know that here will be H1, and this will be H2. So this figure is extremely important because this is the figure that will tell you which table you need to go and use. So if it's in this state, if it's in this region, what is the state? Gas. If it was in this state, will be liquid. And if it's right in the middle, will be a mixture. So basically, we need to go to the gas area. So let's see what would be that table. Alright, so going to table A13, and then you need to look at two things. You need to look at the pressure at P equal 800 kilopascals. And what is the other thing you need to pay attention is the temperature, and 35. So 800 kilopascals, okay, so that will be the same as 0.8 megapascals. So if you go to table A13 over here, let me zoom in. Here you have the pressure 0.5, 0.6, 0.7, 0.8. So over here is at 35, so let's see if you can see. We don't have the temperature at 35 is not given, meaning that we're going to have to interpolate. So we're going to interpolate between the saturation temperature and 40. So I need to find the values for H. That will be 267.34, 276.46. Okay? So let me write these two values over here. So over here we need to do the interpolation. So at T equal T saturation, which is, let's see, 31.31 degrees Celsius, and T equals to 40 degrees Celsius. What do we have? H equal to 267.34 and H equal to 276 0.46. Okay, so here I'm going to refer you to the video about interpolation because I'm just going to do it directly. So basically H1 in this case will be equal to what? H1 will be equal to the 267, I start by the lowest one, 0.34, plus the slope. So what should be the slope is 276.46 minus 267.34 divided by 40 minus 31.31 times the amount of increment, 35 minus 31.31. Again, go back to the videos and you should find one about interpolation. I don't want to spend too much time over here because then it will do the video too long. Okay, so this is equal to 271.212 kilojoules per kilogram. All right. Now the other one should be a lot easier. So let's see, what do we have? The curve, the figure over here. So H2 we know it's just the saturated value for the 800, so we know the temperature. So basically, I guess we can go back to the same table, which is table A12 at P equal 800 kilopascals. Let's see what we have. 800 kilopascals. Pay attention on the top, so it should be H should be equal to H fluid because on that part. So now we need to find out the 800. It looks like it's 95.48. So we'll have over here that H2 equal to 95.48 kilojoules per kilogram. I can square this. All right, so finally, let's just recall this expression over here. So recalling the equation coefficient of performance equal to M H2 minus H1 divided by the power. So let's see, what do we get for this one? So we know the mass flow was given to us to be equal to 0.018. Okay, I'm getting that from this figure over here. Oops, I forgot to zoom out. Sorry for that. Then H2 over here is 95.48. H1 minus 271.212. And this is kilojoules. We have this in kilowatts, so that should be good. Divided by 1.2. So let's see, this will give you a negative value, so that's not reasonable. Okay, I think. So remember that the work going in the textbook convention is negative and the heat going out is positive. So then this is actually minus 1.2. So that at the end, once you do the calculation, the coefficient of performance for this system is equal to 2.635. All right. So now we need to solve. So let's see what I need to solve for. We need to solve for this cube sub L, which is equivalent to this one over here. So if you look at this figure, what do we know? We know that by definition, we have that the power is always equal to the amount of heat transfer release. Later on, we can say that it's proportional to the temperature difference between the hot and the cold reservoir. So if we do this, we are looking for Q dot L will be equal to what? Will be equal to Q dot H minus, so Q sub L without Q H minus the power. So we just calculated the C of P, but we had another equation. Let's see if I find it here. So from the equation, C coefficient of performance equal to Q dot sub H power, we know what? We can say that Q hot will be equal to the coefficient of performance times the power. So that this will mean that the amount of heat going out will be equal to the coefficient of performance times the power minus the power. Or finally, this will be equal to the power factor of the COP minus 1. Okay, so doing the numerical application, what do we have? We found the power to be equal to 1.2 times 2.635 minus 1. And this is going to give us that Q sub L is equal to 1.96 kilowatts. Okay, and this will be the answer. All right, thank you so much for your attention.